Okay, today is September 21st, 2021. Good. So let's go to our notes. This one here. So we did 4 examples for the projectile motion. Okay, and the equation showed that the path is a parabolic path. These equations do not account, let's write that down here. These equations do not account for air drag. Page break. Yes, 09. Okay. The above equations do not account for air drag. Okay? If we account for air drag, it's no longer going to be a parabola. It's going to be very close, sort of close to a parabola, but it's not going to be the parabola per se. It's going to be a kind of a parabola that's not similar to a parabola, but it's not, you don't have a mirror image like you have for a parabola. Okay, I have derived the equations for a projectile subject to air drag. I have derived. It's lots of work. Okay, but we don't do that in this course because it's too extensive to do that. It is possible. It is possible to derive the equation of motion for an object, not projectile, right? That's for an object subjected to an air drag, but the final result is very messy. Okay, and the derivation as well. It's a huge equation. I did that step by step. I even made a simulation so I could picture how the path of the projectile look like. Okay. So let's see. I want to. Oh my. Okay, that's what I want. I want to get this guy here. All those 3, I'm gonna drag right in here. Replace file destination. Let's see. Okay, I want this one right in here. Here you go, my notes. My notes that are Amazon.com. Okay, we are right here in chapter 4. So here you go. I showed all. We went through all the stuff. Let's see if we have one more type of example, right? I did the example of the projectile that we treat all the time. Here you go. That's the projectile motion example. Let's see if we have another example there when we do here. And here you go, projectile. This I plotted in Excel. Okay, with those equations that I derived. Projectile motion. Here you go, equation maximum height. We did maximum height, right? Let's see. Oh, we can do the range. Okay, you can do range and yeah, let's do those because we didn't do this. And let's go back here. Okay, so let's review again what you did. Okay, path of the projectile. Okay, for which angle the particle remains airborne the longest. Right, so I'm gonna copy that and paste down there. So we have 4 have another one here. The equation, we derive the equations of motion. That's the longest one. Equations of motion of a projectile. Notice that they're treating those as though they are problems, right? Okay. I'm gonna summarize down there so you don't get lost and start doing something else that's different. Let's go. Here you go, right in here. We did the following, right? We found the equation of motion of the projectile, determine how long the projectile stays airborne, determine the angle theta, the angle theta for the launch angle, determine the launch angle that the particle remains airborne the longest, and determine the path of the projectile. So that's what we did. But there are other things that we can do too. Okay? One important problem that we usually do is determine the range of the projectile. That's another important problem that we do based on those equations of motion. And what do I call range of the projectile? Okay, range. Do you know how the definition of range? Range, where range is defined as what? What's the definition of range?
Velocity?
Velocity? No. What did you say?
How far something can go?
Yeah, it's defined as the horizontal distance the projectile travels just before impacting the ground. Just before impacting the ground. That's what. Now let me see. The horizontal distance of the projectile. Oh, wait a minute. The horizontal distance of the projectile from the point of launch. So that's a more generic definition. From the point of launch. Okay? But in our case, this range is the distance that the projectile impacts the floor from the place it was launched. Okay? NASA usually define range as the distance, as the horizontal distance that the rocket is. Okay? The rocket didn't impact the ground. But NASA usually define that. So NASA launched the rocket doesn't go in the vertical. The rocket actually describe a curve. Okay? So NASA and every space agency, they report the height of the rocket and the range of the rocket. Okay? So that's their definition. Our definition of range is the point where our projectile impact is the distance, the horizontal distance that our projectile impacts the ground from the point of launch. Okay? So here go, I launch my projectile right in here, boom. It impacts the ground right in here, that's the range. Okay? That's how we define the range. Make sense? Okay? But again, people use this definition of range differently. Okay? So watch out. So how do we do that? Let's see. We gotta do a drawing to understand. Don't try to grasp the problem just by reading it. You have also to make a drawing of your situation so you can grasp the problem more easily. Some problems, you solve 50, 60% of the problem just by making drawings before you even crank in equations. Some problems are just like that. So let's go there to the page. Slides show from the beginning. Okay, let's go one by one. That's gonna be the experiment that we're going to do today and Thursday. That's the vectors. Okay, oh, let's see here. Projectile, right in here. See that? The drawing of the projectile. This is something else. Let's see. Oh, I don't have the more drawings, huh? What a shame. Let me see if I have somewhere else. Yeah, I don't have drawings of projectile here. Might be in another document. Here, must be in this one. Okay, so let's see. Vectors, vectors, head to tail, parallelogram. Go. Components of a vector. Oh, my computer is getting slow. Go. The graphs of motion. Go two-dimensional motion. Oh man, I want to see projectile here. This document is getting too big. That's why the computer is slowing down here. Okay, so that's where the drawings start, right? So slide from beginning, from current slide. Here you go. Okay, parabolic motion. Okay, so the range is this distance here, from here to here. Okay, that's the distance. That's the range. Okay, and so in order to find the range, what do you have to do? You already have your equations of motion. Okay, you already have your equations of motion. What you have to do, you have to find the time of flight of the projectile from here to here, right? Once you find the time of flight, then you plug the time of flight into the equation for the x component. That's how you do it. Make sense? Okay. Okay. So that's the trick of the problem. And what is the condition for the time of flight that you can use? The condition that you use is y equal to 0. And I believe we did that before too, right? Did we do that? I believe we did that before. We found the time of flight. Let's take a look at our notes here, physics notes. Not this one, the other one. Here you go. Determine the launch angle, determine the range, determine how long the projectile stays airborne. Okay? I'm going to put that time t equal to capital T. Okay? Okay? So if I substitute this capital T, which we already calculated in the previous problem, into the equation for x, we are going to find the range. Make sense? Okay? So think about that. Let me get the equations. I have to go back here getting the equations. That's so right now parametric. Okay, that's not this one, right? Okay. How long the projectile stays airborne. So that's the t that we want. That's the t that we want. I'm gonna copy that and paste down here. Okay. Now we're going to determine. Now we are going to determine the range of the projectile. Where range defined as the horizontal distance of the projectile travels from the launch point. From the launch point. Okay. We calculate solution. Solution. we calculated before that the projectile remains airborne during the following period of time. Okay, so here you go. That's how long the projectile remains airborne. Consequently, the range will be the x position at this instant of time. Or, you know, let's get our equation for the x position. Okay, which is not this one, but at this point you should have. Oh, here you go. That's the one. You should have it memorized. Okay, v naught t cosine of theta. The projectile starts from the origin. Here you go. Okay, so here you go. Now what we're going to do, we're going to substitute this t right in here. Okay, and when I substitute this t right in there, the x become the range, right? The range R. Here we go. X, here we go. X at t. Let's put it this way, right? And then I'm gonna change, instead of t2, I'm gonna call it t, capital T. X of at instant of time t is equal to the range, which is equal to that. Put this way. And now it's just a matter of, oops, did I miss anything? Yeah, I did miss something, right? Yeah, the sign of theta is not there, right? Go. Oh, I hate those keystrokes here. Here we go. I don't like mouse pads. Mouse pads are too difficult to work with. Maybe I'm gonna use this mouse here. Okay, so let's try to simplify this equation. The easiest simplification is the V naught square, right? That's the easiest simplification. V naught combined with V naught. That's the easiest one. So I'm going to combine those two, make it V naught square. Okay, V naught square. Okay. And there is something else that we can do to simplify. Now I don't need the, and I'm going to do the following. I'm going to continue the derivation in the previous line. So I can save space. Okay, and now we have to worry about this one here. We can simplify this one as well. Do you know what this one is going to be equal to? How we can simplify this one here? It's one of your trigonometric relations. What? Tangent? No. Tangent is sine divided by cosine, right? Tangent is something divided. This one they are multiplying, right? That would be tangent, right? So tangent is not. Sine square. Huh? Yeah, we have theta repeated here, right? Because we have theta repeated here in the sine and cosine, so it's going to be, you have a sine and you have a cosine. So it's going to be something related to sine of 2 theta. Okay? There are those relations out there in math. But there is more. Sine of 2 theta is in reality 2 sine of theta cosine of theta. Okay? You can see those relations there in math. Okay, so I'm going to do like that. Here you go. Take out this 2 and put right here in front the sine theta. Okay? Like that. And now, This term right in here is going to be sine of 2 theta. Okay? The generic equation, just for you to, remember the generic equation. Sometimes it's difficult to memorize those things, right? But it's important. If you're going to do A plus B, right? Sine of A plus B. Remember that? Sine of A plus B. I have memorized those things. Is what? Everything that's sine, is mixed up with the cosine, okay? That's what you have to remember. So the cosine is more important than the sine, okay? Everything that's sine of A plus something else, there will be a mixture between the sine and cosine. So it's going to be two terms, sine of A, cosine of B, okay? But there must be a second term here as well, a summation. Here you go, gonna have a plus sign, and then what else? I'm going to the second term. That's what we end up memorizing, right? In trigonometry. Okay? For the special case in which A is equal to B, right? This thing reduces to 2 sine of the angle times the cosine of the angle. Okay? That's the special relation that you have to remember. If you had cosine plus cosine of A plus B, it would be slightly different. It's easy to memorize, okay? Just remember that the cosine is more important than the sine in the trigonometric relations. So what we're going to have? We're going to have the first term is going to be cosine of A, sine of B, sine of B, sine of A. But then, because I told you that the cosine is more important than the sine, you're going to have this negative sign here. Okay? That's how you... But we are not using this relation here. We are not using this relation right in here. We are using this relation here. So now we can here write that in a simpler way. Okay, range equal to... Okay, this guy becomes sine of 2 theta. And everything else disappear. Okay, that's the equation for the range. V dot square over G, sine of 2 theta. Okay, so let's go for another example. Here you go. This one is going to be example 5, right? Example 5. Example 5. How to determine, that all sorts of things that we can do. How determine, or not how, determine the range of the projectile. Okay. There are all sorts of examples that we can do with those sets of equations, with those equations of motion of the projectile. We can go for another one. Here you go. Example 6. Determine. Example 6. Given a launch, a fixed launch angle theta, comma, no, sorry, given a fixed launch speed, okay, not launch angle theta, launch speed v naught, comma, determine the angle of longest range. You already should know the answer for that, right? If you want to kick a ball the further possible, what's going to be the launch angle of the ball? What angle must you kick? Huh?
45.
45. right? If you manage to propel the ball at 45 degrees, it's going to be the longest range that you can get for the same speed. Okay? Of course, if you give a kick, a harder kick, the ball is going to go further away, right? But we're not talking about that. We're talking about a fixed launch speed. Determine the angle of longest range. Okay? So how do you do that? Solution. Okay? We want to maximize R for theta. That's what we want to do. We want to maximize R for theta. You know, which theta will maximize R? In other words, which theta will maximize R? That's what we are asking here. Okay. So go ahead, look at this, copy and paste this equation right in here. And then you look at your equation. Here you go. You have a sine of 2 theta here, right? That's the function that needs to be maximized. That's the which value do you want this function to have? 1, right? That's how you maximize the assigned function, right? Okay, to maximize the above relation, we must have sine of 2 theta equal to 1. Sine of 2 theta equal to 1. You already know that's 45 degrees, right? Now I'm going to prove mathematically that this thing is 45 degrees. Okay? We must have, I'm going to put in the next line, we must have oops. Okay. This happens only if the argument of the sine is how many degrees? The argument, the whole argument of the sine. What angle 2 theta is supposed to be for something like that to hold? I'm asking the whole argument, not just the theta. Okay? So here you go. I'm going to rewrite it here. Instead of sine of 2 theta equal to 1, I'm going to put sine of 2 theta is equal to 1, which is equal to what? Yeah, pi over 2 or 90 degrees, right? I'm going to put 90 degrees. That's easier for me. Right? That's what 1 is, right? 1 is sine of 90 degrees, right? Do you see that now? You knew that's how you maximize sine of 2 theta. And it is 1. And 1 is also can be here written as sine of 90 degrees. And now that you know that sine of 90 degrees is equal to 1, which, by the way, must be equal to sine of 2 theta, now you can solve your problem more easily without making a mistake, right? Here you go. That's the relation that you have. Okay? So what do we do next? Now we make the argument equal to each other. 2 theta equal to 90 degrees. Okay? Can you solve that now? Can you finish that? That's easy, right? Theta equal to 45. Okay? In order for theta to be equal to 45, 2 theta must be 90, right? So that's the longest range that we get for the projectile. 45 degrees. Let's see what else we can do. What else we can play with. Let's go to my notes. Okay, there is one more interesting problem that we can solve. Maximize the range. Okay, the question, the next problem I want to pose to you is, are there any two different angles, that result in the same range? If so, what are these angles? Okay, that's the next one. Suppose I launch a projectile at theta 1 and it goes to a given range. Do we have a second launch angle that would result in the same range? That's what I'm asking. Okay, let me see if I have it. I don't think I have one here. No, I don't have it. Okay, so if angle theta results in this range, is it possible to find another angle theta that would result in the same range? That's what it is. A different launch angle that would result in the same range. That's what I'm asking. Okay? And let's solve this problem. Notes, go back here. Okay. Example what? 6? 7? Are there any two different angles that result in the same range? If so, what are these angles? Okay, solution. Let's go. What is the starting point? That's the starting point here. Okay, that's the starting point. Range is equal to that. So mathematically, I'm asking the following question: are there two different angles with the same range? That's what I'm asking mathematically. Are there two different angles with the same range? Okay, like that. The velocity is going to be the same, the gravity is going to be the same. That's what I'm asking. If, something like that exists, what would be the relation between those two angles? Okay? So, if it's possible to solve this equation, right, this equality is going to hold. If it's not possible to solve this equation, this equality is not going to hold. That's what we have. Can we have this, not... Okay. How do we do that? Think how we're going to do that. We gotta go to the trigonometric circle. Let me see if I can find it. We have to go to the trigonometric circle to solve this problem. That's the trigonometric circle. No, that's a circular motion. Okay, maybe I have in the other slide. Let's see. PowerPoint must be maybe this one here. If I don't have here, I'll have to draw from scratch or do that in the board. Okay, it looks like it's this one here. Yeah, that's the one. Okay, that's the trigonometric circle, right? I'm gonna do it step by step here, so you don't get overwhelmed with all those symbols. I'm gonna take out the trigonometric circle. Everybody knows about the trigonometric circle, right? And here we go. I don't need that. Now we start with the x and y axis. See, all those tricks that we learned in high school about the trigonometry, we're using it now. And what about this one? Why it doesn't? Okay, good. Good. X and y axis. Right? Go ahead, draw it. And then you're going to draw also the trigonometric circle. Again, I don't want to overwhelm you, so I'm not going to put sign yet. Sign is going to come later on. times that, 535. Okay, almost there, right? So here you go. First is this one, right? The x and y axis. Then you put the circle there. Because it's the sine circle that we're interested in. Okay, let me take out the numbers as well. I want to do this step by step. The number is gonna come afterwards. Okay, here we go. Sine. Here you go. Next. Okay, now that we know is the sine circle, we can put the values along the sine circle, right? It's going to be 0 here at 0 degrees, 1 at 90 degrees, 0 at 180 degrees, minus 1 at 270 degrees, right? Next. Oh no, I missed them all. Let me go back here. Okay. Okay, now I'm gonna make copies of this guy. Okay, so I can remove that. Okay, next. Okay, so we have, suppose that we have, oh, not only we have the 0 and 0, but now I'm going to indicate the signs of the angle. This quadrant is going to be negative, this quadrant negative, positive, positive, right? Goes from 0 to 1 here, 1 to 0 here, 0 to minus 1 to 0. Okay, you know that, right? Everybody knows that. It's positive on the top two quadrants, negative in the lower two quadrants. So what's next? Okay, so suppose that we have a given launch angle. I'm not gonna call it theta, I'm gonna call it phi 1. Okay, suppose. So what do we want to do? We want to find a second angle that has the same value for the sine. Okay? And that's what the next slide is. According to the trigonometric circle, that is a second angle that you get exactly the same value for the sine. Okay? And this angle I'm calling phi 2. Phi 1 has one value and phi 2 has the same value, but those two angles are different. Because, why does it happen? Because of the symmetry of the trigonometric circle. Okay? Because the symmetry of the trigonometric circle. Now let's investigate this trigonometric circle. Right? So this phi 2 is different from phi 1. However, its complement, the complement of phi 2 is equal to phi 1. Do you see that? We can write down that phi 2 plus phi 1 is equal to what? 180 degrees. Okay? So that's the trick. That's the trick. You have to use your tool, right? Your toolbox, your mathematical toolbox that you learned back in mathematics, in trigonometry. So now we can continue our, here you go. And I'm gonna write like that now. Instead of writing 2 theta 1, I'm gonna write down as phi 1. Okay, I'm gonna put here phi 1 without the 2. I'm gonna erase the 2, don't worry. Let's see if I can get the phi here. Yeah, I have a phi here. Good. No, number 2. Oops. Here we go. 2. We also know now from the trigonometric circle that phi 1 plus phi 2 Again, tell me again. You told me before. Is equal to what? 180. Yep. I'm going to erase this sign very shortly. Don't worry. Okay. Or let's say it's equal to pi, right? I'm going to put 180. That's easier for me. Let's use this guy here to simplify my work. 180. And copy and paste. Okay? And now I can write one in terms of the other. I can write one angle in terms of the other. I'm going to eliminate phi 2. In order to eliminate phi 2, I have to write phi 2 in terms of phi 1. That's how we eliminate phi 2. Minus phi 1. Okay? Now remember what I call phi 1 and what I call phi 2, right? Phi 1 was 2 theta 1, right? And phi 2 was what? 2 theta 2. Have you ever seen that in a book? I've never seen that solution in a book. I had to invent that myself. Have you ever seen a physics book with this solution, step by step, the mathematical step by step? I have never seen it. I had to invent that myself, believe it or not. And I have been teaching for what, 10 years already? 20 years, I would say. Okay, here you go. So what else can we do? Books usually just tell you, because of the equation of the range, you're going to get the same range if the angles sum up to 90 degrees. That's what the books, but they never prove it mathematically. I never see that. But my notes has it. Go. Sum. Right? That's the relation between them. And now I can divide both sides by 2. And that's what I get. Okay? If theta 1 plus theta 2 is equal to 90 degrees, then, both angles will have the same range. Okay, example. The 10 degrees and 90 degrees. Not 90, sorry. 80 degrees. Right? You sum those two angles, you get 90 degrees. So if you launch a projectile at 10 degrees, it's going to get that range. If you launch a projectile at 80 degrees, it's going to get the same range. Okay? You're going to get the same range. Next. 20 degrees and what? 70. Those two ranges are going to be equal. But this range is going to be different from this range here. Okay? Okay, so range 1. I'm going to call that range 1. 10 degrees and 180 degrees. Range 2. 20 degrees and 70 degrees. Range 3. 30 degrees and what? 60 degrees, right? So on, right? 40. I don't have 50 here. Oh yeah, I have 40 and 50. And the last one that I like to show you, is 45 and what? Yeah, 45 and 45. 45 and 35. 45 sums up 90 degrees with another 45. Okay. So 5:45, and I think we can have a break, right? So let me take attendance first. I want to pause. Remind me to start it again, okay? You pause. Okay, the limit for problems is just the imagination, okay? So let's see if we can find another one here in my notes. Yeah, here you go. See it, the trigonometric circle. Okay, now we're going to talk about uniform circular motion. So we exhausted the problems on projectile motion. Now, what's going on here? Interesting. Why is not showing? Huh. You're supposed to show the things here at the bottom. I don't know why it's not showing. Okay, so here you go. Now, let's see. Is that the one I want or the other? Oh no, my computer is misbehaving again. Okay, so let's see. Now it's working in the way it's supposed to work. Okay, uniform circular motion. Let's start concurrent. Okay, we start with the x-axis. Okay, it doesn't matter if it is one-dimensional motion or two-dimensional motion. You always will have to put the x-axis in there. If it's one-dimensional motion, all you need is one axis. If it's two-dimensional motion, you're going to need two axes. And that's what you're doing now. You're doing two-dimensional motion. And we're going to study uniform circular motion. So uniform circular motion means exactly that. You're going to have a circular motion, a circular path of the projectile. Okay, draw the circular path, radius r. Here is positive r, negative r, negative r, right? X-axis, y-axis. And then you're going to put a particle there in your track, in your circle. Next, what you're going to do? You are going to show the vector position of the particle with respect to the origin. Okay? One more? What else do we need? Okay, you gotta show the angle. What else can you show? Okay, the coordinates x and y of the particle. The coordinates x and y of the particle are changing because it's moving in the circle, in the circular path. Okay. Next, the velocity vector. The velocity vector is always tangent to the path. Remember, just like we saw before. And what else? We also have, we're gonna have also the acceleration, the centripetal acceleration, but I don't see the centripetal acceleration there. Let me see. Okay, now I see it. I gotta fix this drawing here. We don't need that. See the centripetal acceleration vector right in here? Different color. Okay. Because it's uniform circular motion, you do not have a component of the acceleration parallel to the velocity vector, only perpendicular. And what does it mean? It means that the magnitude of this velocity vector will remain constant throughout the circle. That's what uniform circular motion is all about. Okay, so here you go. See, velocity vector here, velocity vector here. The length is the same. Okay, if I didn't get the same length, that's because it was my mistake. Okay, looks like a little bit shorter than the other ones, right? But that was my mistake. Okay, but it's supposed to be the same length for the velocity vector. Okay. So how do we treat this problem? Again, speed of the particle, not the velocity. The speed of the particle is constant. The velocity is not constant. The magnitude of the velocity is constant. That's the difference, right? Speed is constant, but not necessarily velocity, because velocity has a direction. The magnitude of velocity is constant when the speed is constant. Okay? That's important vocabulary here. So let's go start with our equations of motion. It's possible to start, let's see, what's the next one here? Yeah, here you go. Remember, we have x and y components, and it's very convenient to define this arc of angle. We call it S, arc of angle S, okay? The distance that the particle travels along, not displacement, but the distance that the particle travels along this arc, along the circular arc, okay? So, for starters, we can say that the x component of the particle is going to be the radius of the circle, can you see that? Times cosine of theta, right? Right? X is r cosine of theta, and y is what? R sine of theta. Okay, let me see if I have the equation here. Yeah, I have the equation right in here. But it's too early to see the others. Okay. Let me do step by step, otherwise we're going to become overwhelmed. Right, here you go. That's the S. I don't want the S here. I'm going to reorganize this slide. Here you go. That's how I'm going to reorganize. Get this one right in here. Okay. And now, it's a matter of getting the proper... I don't need this one. Oops. So the idea here is to get the equations of motion of the particle, of a particle undergoing uniform circular motion. Okay, and now it's too early for that. We're gonna get there. Here we go. Too early. Oh. Okay. Too small for you? Let's zoom in. R cosine of theta, R sine of theta. I don't need that. Okay. And then what else? We have, you know, I have to show this one here. And I'm going to transport this equation to this slide. Let's not forget. See the path, the arc length S. I'm calling that arc length S. This arc length is related to R and theta. There is a relationship between them. And this relationship comes from the definition of angle, the very definition of angle. Okay? So you should have learned in math that the definition, the real definition of angle, is not that the angle goes from 0 to 360 degrees. The real definition of angle is that an angle varies from 0 to 2 pi radians. And the definition of angle, I'm going to write that down for you, is what? Is the length of the arc divided by the radius of the circle. That's the definition of angle. That's the real definition of angle. Do you have any idea why we came up with this measurement of angle in degrees, and then we forget that the real definition of angle is in radians. There's a reason why we do degrees more often than radians. Have you thought about that? Okay, so that's what you see right in here is the real definition of angle, and that's what you're going to substitute right in here. Have you ever thought why we measure angles in degrees more frequently than with in radians? Have you ever thought about that? No? Has to do with historical reason, okay? Has to do historical. How many days do we have in the year? 300 and? Yeah, is that 360? No, but it's close, right? It's close, right? Back in the antiquity, the Babylons measured the year in 360 days. Okay? The Babylons did that. And then they knew that the year was 365 days, but it was very convenient for them to account for 360 days for the year. And you had like 5 days left, right? That they had to correct later on. Okay, after 6 years, you are lagging 30 days, right? Make sense? Year 1, you're lagging 5 days. Year 2, you're lagging 10 days. After 6 years, you're lagging 30 days. So every 6 years, what the Babylons would do? They would add another month to the year. They're back, the Babylons, their month was 30 days exactly. Months 1, 2, 3, 4, 12 months, each month had 30 days. Okay? And then every 6 years, they would add a whole month of 30 days to keep up with the actual motion of the Earth around the Sun. So every day would correspond to 1 degree, right? Every day of the Earth, the motion of the Earth around the Sun would correspond to 1 degree. That's where the idea of angles came from. Had to do with the calendar of the Babylons. Okay? But the real reason, the real definition for angle is this one that you see here, the one that's measured in radians. Keep that in mind. Now we can go the next step, right? What you're going to do, I'm writing the equations of motion of my particle undergoing uniform circular motion. I still didn't use the idea of uniform circular motion, hang in there, but I'm using the relation for the angle theta right in here. Okay? In the next step, we are going to use what? We are going to use the fact that this particle is moving with constant speed. How do you do that? Okay, to say that the particle is moving with constant speed means that the arc angle is equal to the speed times the velocity. Make sense? Right? And now I can substitute that here at the top. One more slide. Okay, Vt, I'm going to substitute right here. Vt and Vt. We're getting there, right? X and Y position of the particle. Actually, we got where we want. Okay, we got the equation of motion of the particle x equal to r cosine Vt over r. X as a function of t, y as a function of t as well. Okay, so, and then how do I get the rest of the equations? Okay, when we are talking about the equations of motion, we are talking about not just the position, we are also talking about the velocity as well. Okay, so let's get the velocity now. How do we get the velocity? the x component of the velocity and the y component of the velocity. How do we get? We differentiate with t, right? With respect to t. Okay, so let's do that. I don't need that anymore because it's already used there in my x and y. I'm going to differentiate those two to get the velocity. V sub x, we go, V sub x. Differentiate what we have in there. R, cosine turns into sine. Let's not forget that becomes with a negative, get into a negative sign. And then we have to differentiate the argument. The argument is what? The argument is V over R. The result of the differentiation of the argument is V over R. Right? Did I make any mistake? No, right? We're going to do the same for the Vy. And now, in order to make my life simple, I will just copy the Vx there at the top and change the subscript. Vy, the argument remains the same, but now we are changing cosine into cosine. Because we are changing sine into cosine, we no longer have a negative sign here. But we still have V over R. We still have V over R. And I'm gonna go for the next slide. And I'm going to simplify here. Here we go. V and V. Now you have to ask yourself if the x component is really going to be negative or not. I'm going to illustrate that for you folks. Here you go. Here's the velocity vector. I'm going to use the other velocity vector. I don't like this one. Yeah, that's the one I like. Here you go. Let me put it here too. Yeah. Next. Right. Yeah, I don't need that. Yeah, not this one here. Next. Here. I want this one here. Here you go. Now hopefully I don't need the pass S anymore. But I want the velocity vector to be there. So you can see that we do have a negative component for the velocity vector. Negative x component for the velocity vector at this point in the circle. Okay? See, the component here points to the left, right? That's where the sign comes from. And the component, the y component of the vector is positive. Let's go to the next one. So the negative sign makes sense. I don't need my S here anymore. What's next we can do? We got the position vector, right? We got the velocity vector. What's next now? What's the next that we have to do? The acceleration, right? We have to get the acceleration now. That, and then, here we go. I'm gonna copy this one, paste here, and differentiate this equation. Just like we differentiate the first one. Here you go. The x component of the acceleration is going to be the derivative of this equation. Sine turns into cosine. The argument becomes z over r. You differentiate the argument and it goes outside, becomes z over r. right? The sign here remains negative. Am I missing anything else? No, right? And now we are going to differentiate this one, the y component. The cosine becomes minus sine. Oops, I put z here. And then we differentiate the argument. We are left with v over r. Okay. In the next slide, we are going to simplify everything. It becomes v squared. Becomes v squared. V squared. V squared. Like that. Okay. So we got everything that we want. Let me see if there's anything else. Yeah, this is. Oh, there is one more thing I'm gonna show you. Okay, we're gonna look at this acceleration vector here, and I'm gonna do that in the other application. But let's go through the slideshow again. I'm just going to repeat what I did here more quickly. Oh man, take forever. I don't need that. So, oh, see, still saving. Oh boy, I guess the document is too big. Let me see if I can go elsewhere. No, I can't. Oh no. Gosh. Okay, good. Finally, it's saved. Finally. Okay, I'm gonna copy all those things. Now I'm gonna use Microsoft Word. Okay. Uniform circular motion. The equations of motion are. Let's see if I can. Yep, I got them. Yep, I did get it. I wonder if I got the way I wanted. Doesn't look like I did. Oh gosh. Okay, it looks like I have to do it from scratch. Insert. I'll have to retype it, or maybe let me try something else. Okay, that might be the right way. Here you go. Okay, it's not the most efficient way, but that's the only way they let us do it. That's the only way Bill Gates allow us to do that. There you go. The acceleration. There is one more important thing that I want you to understand. Okay, here you go. I'm going to write down those two in, let's see, I guess we don't need to do that. I want you to compare this with this, okay? note that, here you go, when you compare the x component of the position with the x component of the velocity, right? You have a cosine here. You do not have a cosine here, right? So definitely, you know, there is the x component of the velocity is not proportional to the x component of the position. Make sense? Okay. But if you look here at the acceleration, you can see that the acceleration, the x component of the acceleration is proportional to the x component of the position, right? See that? We have a cosine here, we also have a cosine here, right? And what happens to the y component? The y component too, you have the same situation. Here you go, I'm gonna even put it with a different color, if I can. You have the y component as being sine of VTR, and the y component of the acceleration also being equal to, proportional to, sine VT over R. The only thing that's changing here is the sign. This one is positive, this one is negative, this one is positive, this one is negative. Okay, and what changes too? What changes too is the coefficient here, right? But that's okay, and I'm going to tell you why. That tells us that the vector position is proportional to the acceleration vector. I'm going to prove that to you, okay? So here you go. Vector position. Now I'm going to write down in vectorial format. Now I'm going to write down in vectorial format. I'm going to get this guy here. Hopefully I'll be able to get, yep. Copy and paste there. Okay, here we go. R. R is equal to what? X, right? Times x hat plus y times y hat, right? Let's put the hats in there. So everything is according to the notation. Okay, so here we go. X hat, y hat, y hat. Here you go. This way. I don't need it to be bold-faced. And I'm going to go even further. I'm going to state that this x and y position, they are a function of time, right? Here you go. They are a function of time, which is true, right? We go ahead and what am I doing here? I'm going to show to you before you forget why we're doing that, right? What are you doing now? I'm going to write that down here. I'm going to show to you. I'm going to show you that the vector position is proportional to the vector acceleration. Okay? Go. And then you gotta do the other one here too. But now instead of a cosine, it's going to be a sine. Okay, and I don't want it bold-faced. Yeah, I want to be like that. And now I'm going to rewrite my acceleration vector. My acceleration vector is a sub x, a sub y, right? A sub x, you know, is going to be minus v squared over r times cosine vt. A sub y, that's the vectorial notation now. Okay? And I'm going to do something else too. One more step here. Let's see if no, it doesn't fit. So let me see if it fits. Maybe it will fit in the line. What time's that? 6:37. We're almost running out of time. I'm going to put the minus VR square, v square over r, in evidence. Okay, and I don't need, and the minus in there, and here we go. You got it, right? That's, and then I'm going to do something else too. I'm going to put the r in this equation in evidence, just like I did for the acceleration vector. And then I'll prove to you that the acceleration vector is proportional to the position vector. Do you see the proportionality now? See? We have cosine vt in the x direction plus sine vt in the vt over r in the y direction. We have cosine vt over r in the x direction and sine vt over r in the y direction. Make sense? So there is a proportionality here between one and the other, and I can even rewrite it. So from the above, I can say the following. I can say that, let me see how I'm gonna do it. I can say that I'm gonna rewrite that. Here you go, like that. Now I'm gonna be easier on you. Over R, right? Uh-oh. Copy. Okay. I don't need the R anymore because I divided both sides by the big R, right? And I'm gonna do the same with the acceleration vector. And what I'm gonna do, here you go. Big R over VR squared. Oops. And I'm going to do something else too. So this one, we go. Oh, didn't do it. Supposed to do it. Okay, you did it. I'm gonna put the negative sign here, and I don't need that anymore. I'm gonna make this equation for the A and the R. I'm gonna put them side by side so you can see it better. Okay. Copy this one. Paste this one. See what we have here? This relation is equal to this relation, right? This relation is equal to the other one. So they are vectors, they are collinear, but it just happened that one has the opposite direction than the other. So here you go. I can write down that, I'm going to write down like that. What you see right in here is equal to what you see right in here. Okay? And I'm going to go even further. I'm going to define this ratio here. I'm going to define it. I'm going to say that it is the unit of the vector in the radial direction, unit r vector. See? It's a unit vector in reality, right? Take a look. It's a unit vector. If you go back here to this circle, the length of this vector is big R, right? So when you divide this guy by big R, you get a vector of length 1. So what you saw in there, what you see here in this ratio is in reality the unit vector R. And I'm going to accent here. Good. That's how I'm going to write that down. The vector in the unit vector in the radial direction. Okay, r hat is the radial vector in the unit vector in the radial direction. Okay, here we go. Let's continue our derivation here. Okay, so here we go. And what else? There's one more step I'm going to show you. The acceleration vector is going to be minus v squared over r in the radial direction. The position vector is away from the center of the circle, right? Let's take a look here again. The position vector is away from the center of the circle, whereas the acceleration vector has a negative component. Because it has a negative value here, not a negative component, it has a negative value. What does it mean? It means that it's pointing towards the center of the circle, okay? If the r hat points away from the circle, the acceleration vector points towards the circle, towards the center of the circle. Because it's pointing towards the center of the circle, we call this acceleration here the centripetal acceleration. Centripetal is towards the center. How is the time going here? 6:44. We have until, okay, we call that the centripetal acceleration. That's the magnitude of the centripetal acceleration. The centripetal acceleration points in the opposite direction of the position vector. And let's see if I can show that to you here. I believe I showed to you before, right? Oh, right. I believe I showed to you before. Let's see. Might be here in this. Okay, this slide here. This one, I'm gonna put it elsewhere. We already knew that was towards the center, right? Because the speed doesn't increase. But now we prove mathematically through other means that the centripetal acceleration is towards the center. We're gonna go after this one. Centripetal acceleration towards the center. That's what we have for this one here. I don't think we have more than that, really. Let's see if we have all the derivations in my notes here. And of course, it's gonna be in the video too. Oh gosh, still saving my PowerPoint. Yeah, still saving. Let's wait for him. Not responding, see? Ay, ay. I believe that because this PowerPoint slide presentation is too big, I gotta cut it down in several smaller ones. Wait. Any questions? Any questions about that? No?
Professor,
Yeah.
when are you usually going to post the videos?
How I was supposed to post this weekend, right? I
Oh
didn't.
yeah, that's why I was.
I didn't. So I'll try to post it tomorrow. Okay.
Okay.
Including this today. Okay, maybe I should get one of few folks to help me post those things because I was so busy this weekend I didn't do it. Okay, and those videos are very heavy too. Just post that in my YouTube channel. Let's see here. Okay, so you did it. Let me see if we have anything else that I have to show to you about centripetal oh, uniform circular motion. Uniform circular motion, yeah. Particle undergoing uniform. Yep, I did that, right? Here you go, right in here. Centripetal acceleration. Okay, then you have an example. Okay, to find the centripetal acceleration at the equator on the surface of the Earth. Then we have non-uniform. Okay, we gotta talk about non-uniform circular motion, and then we gotta talk about relative motion. Okay, and that's the end of chapter 4. We end chapter 4 next class meeting. Let's see here. Let's see. Blah, 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 blah. I go quicker than that. Yeah, that's right. That's gonna be the last thing. We're gonna do so 2 more things, right, that we have to do before we finish this chapter. So
Don't forget to do another line for that one.
what do you say?
The last formula, the R with the V square over R.
This one?
Yeah, it's supposed to be R, like capitalized.
Oh yeah, it's capital R, right? Yeah, you're right. Let me see if it. Yeah, that's right. It's capital R, not lowercase r. Thank you. Go. Okay, next time. Next time, non-uniform circular motion and relative velocity. So let's stop here.